So do you have any question here in this conversion? You just keep on dividing by 2 in this case because we are talking about binary, right? So when I change your number base 10 system to base 2 system, so that's why we keep divide by 2. If you want to keep dividing by 2, so if you want to change your base 10 to base 8, you keep dividing by 8. If you want to change it to base 16, you keep dividing by 16. Okay, that's a simple rule. All right, so let's move on to the number conversions here. So this is just a summary of what we did previously, but I want to generalize this a little bit. Okay. So this is the rule. Like if you have binary, if you want to change from binary to base 2 to the x, I'm just trying to make a rule here. So if you guys recall from the last lecture, remember we make the group of, suppose you have a binary number, you know, I don't know. So this is the binary number, right? So if you want to change it to octal system, how do you group them? Octal. This is binary. Okay. You want to change it to octal system. 8. So how do you group this guy? So here, the binary number. So you make the group of 3, right? Okay, group of 3. Okay. Why do you choose a group of 3? Because 2 to the 3, x equals 3, right? X equals 3 implies 2 to the 3 equals 8. See that? That's how you choose it. That's the whole idea. Okay. Similarly, if you want to change it to rather to hexadecimal, right? So you want to change it to hexadecimal. Then how do you group them? If you recall it, we make the group of 4, right? Group of 4, and you can put as many zeros as you should. You have to make another group of 4. Make add 3 more zeros here. So group of 4, group of 4, group of 4. Okay. Then, so why do you choose the group of 4? Because according to this rule, what is 2 to the 4? 2 to the 4 is x equals 4, right? So 2 to the 4 is 16. So that's the base 16. That's the general rule of converting binary to octal, hexa, and so on and so forth. Okay, this rule can be extended. Okay, that's what I'm trying to say here. Okay, so yeah, this is the same thing, but in the inverse order. Okay, so from base 2 to the x to binary. Now let's talk about the binary addition. So binary addition. So as we do in the normal addition in decimal system, we do the similar thing, but in this case we have just 2 digits, so it might look a little different, but it's not difficult. Okay, it's very easy. So suppose we have 2 binary numbers here. I have a binary number which is 0, 1, 1, 0, 0, and this is the other binary number. If you want to add them together, because what is your binary system? In the binary system, you have 0 is this is your decimal, let's say. This is your decimal, this is your binary. Okay, 0 is 0, 1 is 1, then 2 is 10, 3 is 11, 4 is 100, okay, so on and so forth, right? So what is 1 plus 1? 1 plus 1 is 10, right? Because if you add 1 and 1 here, right? If you add 1 and 1, you get 10. So that's why you have 0 in here, you have 0 here, this 0, and you have the carry 1. Okay, so similarly, 1 plus 0, which is 1, and this carry 1 gives you 10. Gives you 10 and the carry 1. Okay, similarly, 1 plus 0 is 0, and this carry 1 gives you 10. Okay, this is 0, then you have carry 1. Then you have 1 plus 1, 10, right? 1 plus 1, 10, plus 1, 11. So you have 1 here, and the carry goes here, 11, right? So you have 0 plus 0, 0 plus 1 is 1. So does it make sense? Guys, question here, please. Okay. Similarly, if you want to add the binary addition, so binary numbers, then what do? Let's say you have a one of the binary number like this, which is 10110, and the other binary number is this here. Okay, so if you want to find the difference, then what do? In the way we do in the case of a decimal system, right? So we use the same table again. Okay, same table here. So if you subtract 0 from this 0, you get 0, right? If you subtract 1, this 1 from this 1, you get 0. If you subtract 1, 0 from 1, then you get 1. Then 0, 0, 0, 1, 1, 0. Okay? This is normal subtraction. We don't have to carry the, you don't have to take the carry, okay? You don't have the carry here. This is the normal one. Now, if you have, so you don't have to take the borrow rather, okay, not carry. So if you want to take the borrow, right, so this kind of problem here, down here, suppose you have a number 0, 1, 0, 1, then you want to subtract 11. Okay, what is 101? 5 is 101, right? So 101 is 5. This guy is 5. We know that. And this 11 is 3. So you are subtracting 3 from 5. So your answer will be 2, right? We know that. So how do you do this in binary? Okay. So you just first let me do one by one. So this one, let's start here. 1 and 1, which is easy, right? This is what I've done here. So 1 minus 1 is 0. That's easy. Then you have a 0 here. So what do you want? So 0 here, 1 here. So how do you subtract 1 from 0? So you have to take the carry, right? So bring this over. This 1 becomes 0, and you carry this 1 here. And when you carry this 1 here, it becomes 10, right? Okay. So 10 is basically 10 is 2, right? So 10 minus 1 is 1. Now you have this 0 here, 0 and 0 is 0, 0 and 0 is 0. So that's what we have here. So what is 10? 10 is 2. Okay. Again, if you do multiplication, it's the same thing again. So 1 times 1 is 1, 1 times 0 is 0, 1 times 1 is 1, 1 times 1 is 1, 1 times 1, you know. Similarly, you add them all together the way we do in the regular mathematics base 10 system. You know, you add them all together, you get this. Okay, this is a multiplication. Next question here, please. All right, so this is just a story for you to read. Okay, so can anybody read it to me? I'm feeling lonely. Please, can you please volunteer, anybody? Read this story, please. Guys, hello? Hello?
I'll volunteer. Okay. There we go. Sorry. Every piece of data your computer works with, every instruction, every number, every MP3 song, every mutant zombie, every video, everything has to be represented as a really, really long sequence of zeros and ones. Your CPU reads and understands only patterns of zeros or ones. Your RAM can hold billions of symbols, but they're all zeros and ones. Your HDD may hold trillions of symbols, but even if you have hours of video stored there, it's only zeros and ones. Each symbol that can be either a 0 or 1 is called a bit.
Thank you.
No problem.
So you reminded of my old days. All right. This is just a short story to make it fun. All right. This is how computer works actually. Okay. All right. So let's talk about the coding now. Coding, when I say coding, is not a computer, real computer language. Okay. So when I say coding, is the binary coded decimal system. So far, so let's try to summarize. Let me try to summarize what we did so far. So 0, it represents on, right? Or I will say the other way around. So in the computer or any electronics, on is represented by 1. On represents 1, I would say that way. On represents 1 and off represents 0. Because computer just understand, 0 and 1, right? So how do you make that guy make understand 1 and 0? So if some circuit is on, it means it is 1. If it is off, then it is 0. Okay. So this is how computer understand. But we human, we are we are used to 10 base 10 system, right? 0, 1, 2, 9. All right. So and the thing is, we have a debate now. So computer doesn't understand this. Computer doesn't understand this. It's very difficult for us to convert everything to this kind of thing. So we are trying to find the compromise in between these two. So for that compromise, it's a binary coded decimal system. Okay. So for the binary coded decimal system, we can represent the number only. In this code system, we just represent the numbers, meaning we can represent 0 through 9 only. Okay. Here we can represent 0, 1, through 9 in this binary coded decimal system. Okay, so and it consists, we take 4 bits. Okay, so we always take 4 bits in this BCD, always. Okay, in BCD we take 4 bits. So number 1, we can represent 1 through 9, sorry, 0 through 9. We can represent 0 through 9. Number 2, it has 4 bits. Okay, in this system, binary coded decimal system. So if you have 4 bits, right, how many numbers you can represent by using 4 bits? 2 to the 4. Okay, so by using 4 bits, so there are just simply 2 bits, right? 0 and 1. These are 2 bits, right? So 2. There are 2 of them. So if you use 2 of these, 4 of these, then you have 16 combinations. Okay, you have 16 combination. So by using 4 bits, we can represent 16 numbers. So in principle, you could represent 0 through 15 by using 16 numbers, right? But in this binary coded decimal, we just represent, we cut off here, right here, which is 9. Okay, we don't go beyond 9. Okay, so this is exactly similar to conversion, but there is a difference. I'll show you. So first of all, let me try to represent digits 0 through 9 by using BCD. So 0 is all 4 zeros. 1 is 0, 0, 0, 1. So you just keep padding the front by 0. That's it. It's otherwise simply conversion. Okay, so just padded the front with zeros, make it 4 digits, right? So these are all the, this is the representation of digits by BCD. So 0 through 9. In BCD coding, what we do is we code the number. Let's say 0 to 9 is same thing, right? We don't see any difference, 0 through 9. Okay, so 0 is 0, 1 is 1, 2 is 10, 3 is 11 with padded 0 in the front, 4 is 100, so on and so forth. 9 is 1001. Okay, how about 10? Because BCD does not represent beyond 9, right? If you want to represent 10 in BCD system, okay, it's like this. So we have 0 through 9, right, in the decimal system. So how do you represent 12? How do you represent 12? We use 1 and 2, right? It's like that. So in the BCD, we have 0 through 9, but if you want to represent 10, then what do you use? You use this 0, 0, 0, 0. Oops. First, you have to represent 1, which is 0, 0, 0, 1. Then you have to represent the 0, which is 0, 0, 0, 0. See, if you want to represent 10, you have to use 8 bits here. 1 is 0, 0, 0, 1, and 0 is 0, 0, 0, 0. That's how you represent 10 in BCD system. Okay, if you want to represent, let's say 13, right? How do you represent 13 in BCD? So 1, first represent 1, which is 0, 0, 0, 1. Then you have to represent 3, which is 0, 0, 0, 1. So in other words, you do bitwise conversion. So which is different from the real conversion, right? In the real conversion, we don't do bitwise. So in the BCD, you do bitwise conversion. Does it make sense?
Yes.
Okay, so very good. Now, now the thing is, the BCD code is the numeric code. As you can see, it just represents 0 through 9, right? It doesn't represent anything else. So 0 through 9, which are just numbers. Okay, so how about the other characters like You know, we represent a lot of stuff in computer, right? If you want to write your name, then you need your alphabet, you know, not only alphabet. Okay, so you need numbers, you need alphabets, you need, you know, symbols, a lot of stuff, right? This list goes on and on. Okay, so now this is BCD is just a number. So how about other stuff? So how do you represent other stuff in computer? Okay, so BCD is one example of numeric code. Okay, so BCD is one example of numeric code, numeric only. It represents numbers. That's why we call it numeric code. Now we need not only numbers, we need some other thing also. So that kind of code is called alphanumeric. Okay, alphanumeric code. So it represents both numbers and the alphabets and symbols. Okay. So one of the most popular, I would say widely used rather, okay, in that sense it's popular too. Yep. So one of the most popular representation in computer world is Ascii code. Ascii, okay. Ascii code, this is the acronym for American Standard Code for Information Interchange. Okay, so American Standard Code for Information Interchange. All right. So in Ascii code, we use 7 bits. Remember in the BCD, how many bits do you use? BCD, we use 4 bits, right? We use 4 bits. Now in this Ascii, we use 7 bits. Instead of 4, we use 7. Okay. So if you want to represent 0, then you have to write like this: 0, 0, 0, 0, 0, 0, 0. This is how you represent 0 in Ascii. 7 bits. So if you have 7 bits, then how many characters that you can represent by using 7 bits? 2 to the 7, right? Okay. So what is 2 to the 7? So 2 times 2 times 2, 2 times 2 times 2, 2 times 2 times 2 times 2, right? So this is 8. This is 8. This is 8 times 8, 64. 64 times 2, 128. Okay. You can represent 128 characters by using 7 bits. Okay. So, but ASCII, even though, because remember most of the time we use byte, right? So did I say that in the, did you talk about? Yeah. So we use byte, right? Byte. What is byte? What is the difference between bit and byte? Bit is just 1 digit, right? Either 0 or 1 is bit, and a set of 8 binary digits is called byte. Okay, so I forgot to mention that. So here I say the 7 bits, but most of the time we talk about byte. Okay, which consists of 8 bits, right? 8 bits. So now if you want to represent ASCII code in 8 bits, which is 1 byte, right? So then you can simply pad the front by 0, extra 0. Okay, so that the leftmost digit is called MSB, most significant bit. Okay, MSB, and of course that will be always 0 because ASCII uses just 7 bits. If you want to make it a byte, then you can use 1 more 0 in the front, but it doesn't. It is useless, kind of useless, right? It doesn't work. I mean, it doesn't. It's just, you know, making the you know, make this fancier. Okay, that's it. Okay, so now we are a little excited that we can represent 128 characters, unique characters, by using ASCII code. Okay. So what happens is when you enter a letter or number or control command or whatever, or shift or something, the corresponding ASCII code goes into your computer. That's how it works, okay? Well, this is how computer works. Now, but the thing is, nowadays we have way more characters that we can represent in computer than ASCII and BCD, right? You already know that. So you can represent all kinds of characters in computer, not only numbers and some, you know, particular characters. It has a whole lot of stuff, okay? So to represent that, scientists just keep on developing new kind of code, okay? So the currently the mostly used code is called Unicode. You must have heard it, right? Unicode. Okay, so it uses 16 bits. So Unicode system uses 16 bits. So we have BCD 4 bits, then ASCII, you have 7 bits. Now Unicode, now it uses 16 bits. Now can you help me here? How many characters can you represent? Can be represented by using Unicode, 2 to the 16, right? That's a lot, okay? So right now, so this Unicode can represent more than 65,000 characters now, okay? It's a lot. So these are some of the examples of Unicode, sorry, ASCII code, okay? So here, if you represent 0, okay, if you represent 0, it's not a normal 0, okay? It has some other rules now. So if you want to represent 0, how do you represent 0 in ASCII code? You simply put 0011, the first set, the second set is 0000, okay? For some reason, we choose the first set to be 0001, okay? Second set makes sense, right? It's 0000, and the first set is a little different, which is 0011. So similarly, 1, the first set goes the same, right? It's the same thing, first set of binary numbers, binary bits, bits. First set is all the same, 0011. So let's go all the way to 9 here, okay? So this is all same, right? 0 through 9, first set of binary numbers is 0011. And how about the second set? Second set is 0000. You know, the first 3 are, you know, not first 3. So I would say this way. So this is all 0, this is 0001, this is 0010, and so on and so forth. This is familiar to us, right? This is not, you know, something that we never heard of, right? So similarly, if you want to represent uppercase A in ASCII, uppercase A, then how do you represent uppercase A? 0100 and 0001, okay? So in computer, right, when you type, if the computer uses, or any electronic device that uses ASCII code, right? Any electronic device that uses ASCII code, if you type A, if you want to type A, then so 7 different, okay, so the first one is on, right? This is first one is on, then off, 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 on. Yeah, it has no meaning, right? The very first one doesn't have meaning because ASCII is just represent, you know, ASCII just has 7 bits, right? The first is just padded there, okay, to make it a byte. So you have on, off, 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 on, and obviously if the first one is 0, okay. So the last one is 0. This one. All right, this is how it represent, how the characters are represented in an ASCII system. Okay, if you want to represent space, then you have the computer sends the this information 001 0000. This is how the ASCII code works. Similarly, this is the ASCII code in hexadecimal. Okay. So in the hexadecimal system, this is how the ASCII code. Let's say if you wanna represent m, little m, right? Let's say I'll just randomly choose one letter here. Then how does this little m represented in hexadecimal system? You have to put, you do 6 and D, okay? 6 and D represents m, okay? So if you want to find what are the zeros and one for this set, you can go to the conversion, right? This is hex. You can do the conversion from hex to binary. Then you see all zeros and one, okay? So little m can be represented by 6D, which is hexadecimal. If you want to see the details, what this guy is, all the zeros and ones, then you have to change hex number to binary, okay? So this is the ASCII code for hexadecimal system. Guys, and question please.
Looks good to me.
Okay, thank you. Now, so far we discussed about different kind of binary representation. So, okay, so we talked about numbers, right? How to represent numbers, how to represent, you know, alphabets. We talked about how to represent space and stuff like that. But we are missing one thing here. We missed one thing. How do you represent? Okay, we talked about numbers, but how are sign numbers? How do you represent plus and minus then? Okay, so let's talk about that here in this slide here. Okay, so the negative numbers in okay, in the computer coding, right? So negative numbers in binary system is represented by 1, while the positive number represented by 0. Okay, but you have to find a way to accommodate that. Okay, we'll find that, figure that out. Okay, so there are mainly 3 representation for the signed numbers. If you want to represent, so this is actually what computer does nowadays too, as far as I know. Okay, so the thing that I'm going to talk about is what computer uses nowadays to represent signed numbers. Okay, so there are mainly 3 representation. So one is sign and magnitude representation, or in short we call it SAM. So in this sign and magnitude, so magnitude we don't have a problem because we already have been doing representing magnitude, right? Let's say, so what is 1? 1 is 1. What is 0? 0 is 0. Okay, this is, let's say, this is base 10. This is base 2. 2 is 10. 3 is 11. And 4 is 100, and so on and so forth. So how about negative 1 now? Negative 1, how do you represent negative 1? You should do you should do 0. You have to pad 0 in the front. Okay, here we had to put a 0 in front here. Sorry, minus 1 here. So let's say, let me write it a little more differently here. Excuse me. So right here, let me erase this. So let's say I represent my 0 as this. I use 1 byte. How about that? 0, 0, 0, 0, 0, 0, 0, 0. Okay. So this is my 0. Then 1 is 0, 0, 0, 0, 0, 0, 0, 1. That's my 1. Okay. So 0, 0, 0, 0. Then my 2 is 0, 0, 0. Oops. 10, right? This is my 2. 3 is 0, 0, 0, 0, 0, 0, 1, 1, right? So 4 is 0, 0, 0, 0, then 0, 1, 0, 0. That's my 4. Now, what is the negative number of 0 then? Negative number of 0 is 1, 0, 0, 0, 0, 0, 0, 0. That's the negative of, oops, negative of 0 is, oh, Okay, that's fine for now, because it's the same thing, but okay. So it's the same thing. If you want to represent negative 0, you have to represent like that. If you want to represent negative 1, you might ask me a question here, but I'm ready. So 1, so 0, 0, 0, 1. This is how we represent negative 2 now. Negative 2 is 1, 0, 0, 0, then 0, 0, 1, 0. See, this one is same. 1 is the front one. Instead of 0, you have 1 here. Okay, so the leftmost, right, this guy is called sign bit, and the remaining is magnitude. So you have most significant bit, which is sign bit, and the remaining will be the magnitude. Guys, any question here? I know you have a question for me. No question? Okay. Then I'll ask a question in a bit, in a minute. Okay. So similarly, if you want to represent 5, this is another example here. I have another example. If you represent 5, then you just have a 0 in the front, and this is 5, right? 1, 0, 1 is 5, and you pad the left in the front side of the, you pad the 1 by 0 in the front, right? So that represents plus 5. And if you have 1, that represents minus, okay? So what is the problem now? So this is the question I was about to ask you. So now if you want to represent 0, right? So 0 is plus 0, which is equal to minus 0, right? So how do you represent 0? Do you represent plus 0 or minus 0? If you represent plus 0, this will be this. If you represent minus 0, this will be that. Now we have a confusion here, right? So this is the problem with this kind of sign and magnitude system. Okay, this is confusing. So, and also it is not efficient from computer's point of view. Okay, so that's why we need to develop some other representation. Okay, so the other representation is sign is 1's complement. Okay, so number 1 we have SAM. Okay, we have 3 representation. I just went over 1. So which is SAM, sign and magnitude representation. Number 2 is 1's complement representation. So number 3, I'll be talking about that later, okay? So let's talk about 1's complement form. So how do you represent 1's complement, sign number in 1's complement form? Okay, so now let's talk about the positive numbers. Positive number remains unchanged, okay? If you want to represent plus 1, right? Let's say this is 0, 0, 0, 1. If you want to represent plus 2, okay, it's the same thing again. 0, 0, 1, 0. Okay, plus 3, then 0, 0, 1, 1, so on and so forth. Okay, so how about negative 1? If you want to represent negative 1, then what do you do? Okay, so you negate everything there. So negative 1 will be, so this 0 becomes 1, this becomes 1, this 0 becomes 1, this 0 becomes 1, and this 0 becomes 1, 1 becomes 0. So your negative 1 will be represented by 1, 1, 1, 0. So how about plus 2 here? What is negative 2? So 0 represented, if 0 is 1, 0 is 1, 1 is 0, 0 is 1. So negative 2 is represented by 1, 1, 0, 1. This is how you represent negative numbers in 1's complement form, 1's complement. So conclusion, positive number as is, no change. Positive number, no change. And negative numbers, okay, just invert everything. Bitwise negative, okay? Bitwise not. So change the every bit into different bit. 1 goes to 0 and 0 goes to 1, like that. This is how you represent signed numbers in one's complement representation. Now I'll be, guys, any question? So far so good. Now I'll be talking about 2's complement now, okay? 2's complement. So these are the 3 different representation of signed numbers. Same sign and magnitude, 1's complement, 2's complement. So I'll be talking about 2's complement now. Okay, so before I do that, let me show you how you add the numbers in 1's complement form, okay? Before I go to 2's complement, I'll show you how to add numbers in 1's complement representation, okay? Let's say here, okay, let me show you here. How do you represent numbers in addition? Or it could be, you know, okay, so for now, let me talk about binary addition in 1's complement. Okay, let me hide this for now. Okay, so if you want to add these 2 numbers, what is this number? Let's say this is oh, by the way, so this can be represented as this. So this is 2 to the 1, 0 times 2 to the 1. This is 0 times 2 to the 1 times 2 to the 2. So you can represent like this: 1, 2, 4, 8, 16. Okay, so 16 times 1 is 16. I have 16 here. 8 times 0 is 0. We have 0 here. 4 times 1 is 4. 2 times 1 is 2. 1 times 0 is 0. So add them all together. 16 plus 4, 20, plus 2, 22. Okay, that's the easiest way of converting your binary to decimal. Okay, so you just start with 1 and multiply by 2. 1, 2, 4, 8, 16. That's how you do it. Okay. So then this guy is, so 1 times 1 is 1, 2 times 1 is 1, sorry, 2, which is 2 plus 1, 3. Okay. So if you add these 2 numbers, which is 22 and 3, then what you should be getting? You should be getting 25. Okay, 3 plus 2, this is 25. All right, so let's do it here. 0 plus 1, 1, 1 plus 1, 10. You have carry here, 1 plus 1, 10. You have carry here. Then you have 1 here. Then 1 plus 1, 1. 1 plus 0, 1, 0, and everything is 0 in the front, right? So this guy is 1, 2, 4, 8, 16. So 16 times 1, 16. 8 times 1, 8, plus 1. So what is this guy? So this is 25, right? Makes sense. So positive number is same thing so far, right? But what happens if you have the carry here? Suppose you have some carry. Suppose you have this is 1, right? Then you have to carry this number. You have to add these 2 numbers and you get carry here. In that case, how you add in 1's complement? Okay, that's what I'm trying to show you here. Okay, this is what I'm talking about. Now you are adding -1 and -2, plus 2. So like this. So plus 2 is definitely this one, right? Plus 2 is 1, 0. That's easy. Our -1. -1, first write 1, right? 1 is 0, 0, 0, 0, 0, 0, 1. That's your plus 1, right? And -1 will be 1, 1, 1, 1, 1, 1, 1, 0. That's your -1. That's what I have here. Negative 1 is this guy here. So I'm adding negative 1 to plus 2. I'm subtracting 1 from 2, or I'm adding 2 and negative 1. I can say either way, right? Okay. So what should we get? We should get, you should get 1, right? There is no doubt about it. So you should get 1. When you add negative 1 and plus 2, you get 1. Let's use the 1's complement to find the answer. So this is negative 1, this is 2, right? So let's add them together. So 0 and 0, 1, 0 and 0, 0, 1 and 1, 10. You have 0 here, and you have carry here, right? Okay. Then 1 and 1, 10, 0 here, you have carry here. 1 and 1, 10, you have 0 here, you have carry here. 1 and 1, 10, you have 0 here, you have carry here. 1 and 1, 10, then you can have 0 here, you have carry here. 1 and 1, 10, you have 0 here, and you have carry here. 1 and 1, 10, you have 0 here, and you have 1 here. Now, so the thing is, now you cannot have more than the bits that you initially begin with. So how many bits did you begin with? You begin with 8 bits, right? You have 8 bits. 4 here and 4 here. So now you have the 9th one here. So what do you do with the 9th one? Okay, you bring it down here. Okay, bring it down here like this and add it. Okay, add this 1 there. So when you have extra bit, the 9th one, right? In this case, when you have extra bit, if it is 0, you don't have to worry, because we don't write 0 because 0 is not even a carry, right? If it is 1, then that's the carry, right? So if it is 1, then bring it over here and add this to the, so just erase this one and bring it here and add these two together now. Add them together. This is 1 plus 0 is 1, and the rest all are 0, right? So what is this number? This is 1. Now we got the answer, right? Plus 2 minus 1, you have 1. That's how you get the answer in one's, do the addition in one's complement form. Guys, question please. Question please.
I'm good to go.
Okay. Now let's talk about 2's complement, okay? Let's do 2's complement now. So this is the main problem this is the main problem with the 1's complement. Okay, you have to carry this guy over here, and you have to add it again. Okay, that's the main problem. That's called end around carry. Okay, one of the problem is end around carry. Then the other problem is also 0. It doesn't have unique representation. Okay, so how do this is plus 0 and this is minus 0, but both of them should be 0, right? Because plus 0 is 0, minus 0 is 0. So both of them should be same representation instead of different. So that's kind of confusing. And also end around carry is another problem, as you have already seen. Now that's why we go to the 2's complement now and see how it works now. Let's see. In the 2's complement, what you do is we add all the bits. So you invert all the bits and add 1 to the result. That's what you do in the 2's complement. Okay. So let me show you here. Oops. So suppose In the 2's complement, let me write this down here, somewhere here. Let me write this here. Positive number, in the 2's complement, positive numbers remain unchanged. Again, positive number is not a problem. How about the negative numbers? Negative numbers. So you do exactly as you do in the ones complement, okay? So in the ones complement, how do you represent negative numbers? Let's say if it is 2, right? Plus 2 is 0, 0, 1, 0, right? In ones complement, what is plus 2? It's the same thing. In the 2's complement, what is plus 2? It's the same thing again. Now in the ones complement, what is negative 2? Negative 2 in ones complement is 1, 1, 0, 1, right? See, this is 1, this is 1, 0, 1. Negative 2 in 2's complement now. Okay, this is the 2's complement now. So what is negative 2 in 2's complement? 1's complement plus 1. That's the 2's complement, okay? So 1's complement is this, right? Plus 1. That gives you 2's complement. So what is that now? 1, 1, 0, 1. I have to add 1, right? That's how you add, how you get 2's complement. So 1 plus 1 is 10. You have carry 1. Then 1 plus 0, 1. Then you have 1 and 1. That's how you represent negative 2 in 2's complement. Guys, question here, please. You'll have homework problem. Maybe, maybe quiz also. Okay, please try to understand these numbers. This method representation.
So with one's complement, you're kind of just switching the zeros to ones and the ones to zeros.
Exactly.
And with two's complement, you're basically leaving everything the same except for the zeros in the front, you're switching to ones. Oh, not exactly.
No. So in the 2's complement, so this is one's complement, right? Okay, hold on. So how do you represent negative 2 in one's complement? This is how you represent 2, negative 2 in one's complement, right? Because positive 2 is 0, 0, 1, 0. Negative 2 is you invert everything. Okay, I'm talking about one's complement for now. In one's complement, plus 2 is 0, 0, 1, 0. Minus 2 is 1, 1, 0, 1. Now, in 2's complement, so how do you represent negative 2? You take the 1's complement, which is this, and add 1 to it. So if you add this, then you will get 1, 1, 1, 0, which is negative 2 in 2's complement.
Okay. So it's just basically an extra step.
Yeah, where one's complement, then you always add 1 to it. Always add 1 to it. It's the one extra step. Exactly.
Okay. Thank you.
All right. Thank you so much for the question. I was so bored. All right, so now let's add the numbers here. Okay, how do you add the numbers in 2's complement form? Let's do that. Okay, so let's add these two numbers here. So what is 6? Okay, what is 6 in the 2's complement? So 6. First of all, what is 6? 6 is okay. You have 4, 2, 1, right? So 1, 1, 0 is 6, right? So this is 6, right? 1,
Yeah.
1, 0 is 6. Okay. So 1, 1, 0. Okay, let me write it here. 0, 1, 1, 0. That's your 6. So how do you change it to, this is plus 6, right? This is plus 6. How do you change it to negative 6 in 1's complement? Because to find 2's complement, you have to find 1's complement for the, that's your first step. So
It would be 1001.
exactly. So then you have to add 1 more to it, right? So then it will be 1 plus 1, 10, carry 1, then 1, 0, 1. So that's your negative 6, right? I did it correctly here. 1, 0, 1, 0. That's your negative 6.
So just a quick question. Are these just basically two different ways of showing negative numbers in binary?
Exactly.
Okay. All right. So they are separate. All right. Thank you.
So there are 3 steps, right? 3 methods, right? One is SAM, sign and magnitude. Number 2, 1's complement. Number 3, 2's complement. 3 methods.
Okay. What was the SAM's method again, if you don't mind me asking?
Sure. So in the SAM's method, you just represent, you know, the as usual, right? So suppose your 1 is 0, 0, 0, 1, right? 2 is 0, 0, 1, 0.
Okay.
So in SAM's method, so this is your plus 1, right? This is your plus 1. This is your plus 2. If you want to represent minus 1, plus never problem. We never have a problem with the plus because it's the exactly same all the time. Okay. So the negative number, if you want to represent negative 1 and 2, let's say, how do you represent your negative 1 and 2 here? This is your plus 1 and plus 2. Here, negative 1 will be 1, 0, 0, 1. Okay, negative 2 will be 1, 0, 0, oops, 0, 1, 0. See, for the plus, you have first one 0, right? 0 and 0 for the plus. For the negative, you simply change this 0 to 1, 0 to 1. Okay, this change.
Oh, so you're always just switching out the first.
Yeah, just the very first one.
Oh.
Just
Okay.
the very first one. Yeah. The leftmost, right? The leftmost. Just switch the leftmost. If it is 0, the computer understands that is positive. Okay. If you change the first one to 1, then computer understands that to be negative.
Wouldn't it also think that it would be, which one's that? Wait.
Oh, okay. I see what you're asking. So
Right. Wouldn't it think it would be the, sorry, wouldn't it think that 1001 would be 11?
yeah, that's what I'm okay. Yeah, because you are trying to define, you are telling your electronic device that you are using SAM system, right?
Okay. All
Okay,
right.
so it won't be confused.
I see why it's a little confusing.
Yeah, you have to tell this guy that, okay, I'm using SAM system, okay?
Okay.
Yeah, you have to develop everything on the basis of SAM. But nowadays I don't think anybody uses SAM system. This is just I'm just trying to follow chronological order.
Right.
So most of nowadays I think every computer they use 2's complement. Okay, everything is 2's complement now because this is so not confusing. Okay, so Now negatives, now you understand how we got -6, right? Now 5, how do you represent 5? It's the same thing. There's no any change. This is 1, this is 2, this is 4. So 2 times 0 is 0, 1 times 1, 1, so this is 5. This makes sense. If you add them together, then what do you do? If you add them together, you just add 0 and 1, which is 1. 1 and 0, 1, right? 0 and 1, 1, and 1 and 0, 1. So how do I know this guy is -1? I simply wrote here -1. I know you will be convinced this is negative because this guy is 1, right? So the first one is 1, that's why this is negative. I suppose you guys convinced so far. But the thing is, how does this guy represent 1? Okay, negative is understood, right? Because the front one is 1. But how does this guy represent 1 then? The rest of these 3, how does this represent 1, right? This is negative, this is 1, becomes -1. So if you want to convert what this guy represent, okay, obviously this is negative. If you want to change it to what it represents, you have to change it back to 2's complement again. So what is the 2's complement of this guy? First do the 1's complement, right? Then add 1. Okay. So now with this conversion, I know this guy is 1. This guy is 1 because this 1. And obviously this represents negative because the first one is 1. Guys, make sense? Yes, no, maybe, kind of, not really. Okay, so far so good, I suppose. All right. Now let's add these 2 numbers here. So 3 is, this is 1, this is 2. So 2 plus 1, 3. And this is 1, oops, this is -2, right? This is -2. So -2 is, you have to do something different, right? So for the negative, the way you did here. So 3 is exactly same as before. So in 2's complement also. Then -2 is this. If you add them together, what do you do? 1 and 0, 1. And 1 and 1, 10, right? Carry 1. 0 and 1, 1 plus 1, 10. Carry 1. 1 and 1, 10. 0 and 1. Now, you have started with 4 digits, right? You have 4 digits here in the, you are adding 4-digit number. When you add them together, you get the 5th one also, right? In 2's complement, you have to always ignore this 5th one. Simply ignore it. Simply ignore the first one. Then what do you get? Don't worry about this guy. You just get 0, 0, 0, 1. Okay? So what is this guy? This is 1. It is positive or negative? Positive because the first one is 0. Does it make sense?
I apologize. What are we ignoring?
We're ignoring this,
Oh, just like the previous. I see.
the first one. We ignore the, the very, from very leftmost one, I would say, okay? Okay, so you should have just, you cannot have more than what you started with. You started with 4, right?
Right.
With 4, you got the 5th one. So that's why you cannot have it. Whatever it is here, of course, 0 is not meaningful, right? If it is 1, just ignore it. 5th one, it will be always ignored. Okay, simply ignore this guy. Behave that this is not there. Now we are left with this 4. So the first one is 0, meaning the number should be 1. Sorry, plus, okay? 0 means the number should be plus. This number should represent plus. And what number is that? This is definitely 1, so which is plus 1. Makes sense? Okay. All right, this is just this is what I did. So this is the conclusion here. If we have a leading 1, that represents negative. If we have leading 0, the number is either 0 or positive. Okay, that's the conclusion. So in this sense, this number system considers 0 as positive in some way, okay? 0 as positive in some way, okay? So, but it doesn't matter, okay? So this is the conclusion. Or leading 1 is negative, or leading 0 is 0 or positive, okay? So since this is leading 1 here, this is negative. Since here leading 0, this is positive, okay? That's what I'm trying to say. Okay, let's do the subtraction here. Let's do the subtraction then. That's so far so good.
Think so.
Okay, let's subtract 7 from 15. Okay, for instance. So let's subtract 7 from 15. So what should we get? We should get 8, right? So what is 7 in the, how do you represent 7? So 1, 2, 4, right? So 1 times 1 is 1, 2 times 1 is 2, 4 times 1 is 4. So 4 plus 2 plus 1, which is 7. How do you represent 15? 1, 2, 4, 8. So 8 plus 4, 12, plus 2, 14 plus 1, 15. But I said it wrong here. Looks like this is good, but why did I say wrong? Because you have to have exactly the same number of, you have to represent 0 and 1 also, sorry, plus and minus. Eventually, right? When you subtract, you're doing this, right? Subtraction is, so subtract 7 from 15 is same as add negative 7 to 15, right? It's the same thing. That's why, so both of them are plus here in some sense, right? Both of them are plus. So that's why you have to represent using the, you have to have some way to represent plus there. So if you say, if we have minus here, this will represent, sorry, if we have 1 here in the front, that will represent negative number. It will give you the sense of this is negative number. That's why you have to make sure this looks like positive. How do you make it look like positive? You have to add 0 in the front. Because you are talking about plus 15 and plus 7, right? So both of them are plus for now. Now, once you consider, okay, let me read it. So you have plus 15 and plus 7, okay? So you have that. Plus 15 is, what do you represent? 0, 1, 1, 1, 1. That's your plus 15. What is your plus 7? Plus 7 is 0, 0, 1, 1, 1. Okay. Now, plus 15 remains same because you are going to subtract this, right? Now, this 7 has to be changed now. it doesn't look like -7 now because we are subtracting, means it is -7. We are subtracting. So this does not look like -7 now. So how do we change it? Is change it to 1's complement, which is 1 1 0 0 0, then plus add 1, right? So then 1 0 0 1 1. So now you have two numbers. So which is 0 1 1 1 1 and 1 1 0 0 1. So now you have to add them together because subtracting 7 from 15 is exactly same as adding -7 to 15, right? That's why you add them together. Subtraction is adding in this sense. Okay, now if you add them together, then what do you get? So I'm adding this guy here, 1 and 1, 10. Okay, so 1 and 1, 10, carry 1, 1 and 1, 10, carry 1, 1 and 1, 10, carry 1, 1 and 1 and 1, 11, 1, 1, then carry 1, then 1 and 1 is 10. So what do we do here? Guys, I'm done, okay? I'm done. So what do we do here? You started with how many digits here?
5.
5. So how many digits did you get here? 6. That's why you simply ignore this. Okay? When you ignore this, what is the first, leftmost zero? Leftmost bit is 0, right? It means this is positive. Okay?
Just a quick question. Pardon me. Is it only in 1's complement that we would take that extra 1 and bring it down and add it?
Yes.
Okay. All right. Thank you.
All right. So in 2's complement, instead of bringing it down, you add it in the beginning.
Oh, I see. Okay. Cool.
Okay. All right. And you ignore the extra digit if you have any when you add, right? This is the extra one, right? So if you the extra one, you ignore it. After you ignore it, you are left with 0 1 0 0 1 0 0 0. Then this 0 represents the number, the sum you got is positive. And what does this number represent now? So 1 2 4 8, right? So everything else 0, so this is 8. So positive 8. So you got positive 8. That is what you should be getting, right? So 15 minus 7 is plus 8. Guys, question here? If not, I'm done for the day.
I think I'm good.